Hey everyone, Mr. Fugay here, and today we're going to look at some supplemental problems from the 10.7 Alternating Series Test for Convergence video series that College Board's releasing. There were a couple examples 3 and 4, and a few practice problems, practice 2 and 3, that they did not go over in the video. So this supplemental video will provide some instruction on how to complete these problems if you are stuck. So we're going to get started with example number 3 you can see here on the screen. I've also, for the sake of convenience, posted what the alternating series test is above the problem here. So we want to determine the convergence for this particular series here. And so it's, again, a two-step process. Step 1 being that we need to test and verify that the limit as n approaches infinity of the a sub n term, that is the entire series term without the alternating portion of it, must approach 0. So let's go ahead and test that first. So the limit as n approaches infinity of, and in this case, we're only going to look at 1 over n squared minus 6n plus 10. And what that's going to happen here is when you plug in this infinity, you're going to get 1 over a very large number. Keep in mind I use an arrow and not an equal sign there, guys. That means that you're going to get 1 over large, or big on bottom. So what that's going to now infer here is that the limit as n approaches infinity of this function has to then equal 0, which is our first thing we need to check off. But what makes this problem more difficult is the second condition. The second condition says that we need to verify that the a sub n plus 1 term, which means the future term, must be always smaller than the a sub n term for some value at some point. Now, what does that mean? Well, it means that the first term doesn't necessarily have to be bigger than the second term, as long as it eventually does do that. So it doesn't mean the first few terms, and here's what I mean by that. If you take this series and you plug 1 in, okay? So if I plug 1 into the series, what I'm going to get is a positive 1/5. When I plug in the second term, I'm going to get a negative 1/2. Now remember, we're not worried about the plus minus because we know it's going to alternate. But keep in mind that 1/2 is bigger than 1/5. So one might say, well, you know what? This is going to fail because the next term is bigger. But keep in mind that the condition of this clearly says that it doesn't have to be the first term where this happens. It just has to eventually happen. And that's what makes this difficult. If we go to the next term, it becomes 1 over 1. So what's happening in these first 3 terms is it's actually getting larger. But with that being said, look what now begins to start happening. We're going to get 1/5 as our next term, and then we're going to get 1/10 as our next term. So beginning here at a sub 3, okay, and then going to a sub 4, so keep in mind, think that's a sub n, and think of this as a sub n plus 1, okay? When n is equal to 3, it appears that the statement that a sub n must be bigger than a sub n plus 1 is actually holding true. So if we eliminate those first 2 terms, we can actually see that the alternating series test is actually going to work here. So how do you do this? How do you show something like that? Because in the video they said, oh, well, all you would need to do is you plug in n plus 1, which is what I'm doing here, and then mathematically show that this has to then be less than or equal to 1 over n squared minus 6n plus 10. And just to be honest, guys, the amount of algebra you'd have to do here, and then on top of that, the amount of work you would have to show for this is next to impossible to do. So this is not the strategy we want to go about. What we want to do is we want to show that the denominator is getting bigger. Keep in mind that if you look here, it goes from 1 to 5 to 10. We want to show that n is increasing, which means what we actually want to look at in considering here is that we want to show that the derivative n prime is positive. So what I'm going to actually do here is we're going to take the derivative d over dn. We're going to take the derivative of my denominator. And by doing that, when I do this, I'm going to get 2n minus 6. Well, 2n minus 6 is indeed going to be greater than 0, but not for all values of n. It's only going to be when, and again, if I solve this, when n is greater than 3, which is exactly what we figured out when we were over here, is that the value of the denominator will begin to get larger starting at n equals 3, and that's exactly what we have here. So what we've created now is a conclusion, and what does this conclusion tell me? The denominator is increasing, and that means that the fraction is smaller. We've done now enough justification to be able to show that this is going to work. So what our conclusion is going to be is that when n is greater than 3, our series, I'm just writing it out now to be official here, will converge. It will converge. Okay. So this is our second check mark. So another strategy here is that you can show that the derivative in this particular case is positive, which shows that the denominator is getting larger. So for the next part of this video, we're going to look at example 4 that was a brief explanation for part B, but we're going to talk a little about it. So we want to determine if the alternating series test can be applied. So before you even go through the official alternating series test, you need to check that that letter A, it's actually an alternating series. So that's the first thing we should probably look at. And then, and only then, do we then apply the test. So you'd apply the test, and then, of course, you check for those two conditions. And I'm just going to scroll up, and I'm actually going to move this down here because this is basically what you would do. I don't even need to rewrite it. So you would just apply the test that we've been talking about here, testing that the limit a sub n is equal to 0, and then a sub n plus 1 is less than n for some value of n on the interval. So looking at A here, what he briefly mentioned is that this term up here is hidden, okay? But this is actually an alternating term. And why is that an alternating term? Well, that was what you want to come back down here to look at, okay? When you plug in 1 pi, 2 pi, 3 pi, what you'll notice is it will always rotate between 1, -1, 1 and -1, and then it will continue that process. So what we can essentially do is that we can substitute the cosine pi over n out, and we can, in its place, put -1 raised to the n, which is that alternating term. We've confirmed it alternates. Then and only then can we begin applying the alternating series test. So condition number 1 is that you need to check that the term, the a sub n term, is equal to 0, which is confirmed down here in blue. 1 over n factorial is going to give you 1 over big, which is going to equal 0. The next thing we want to do is we want to plug in n plus 1. And I just mentioned a second ago about the derivative strategy. That would be a strategy that would not work here because of the factorials. But what we can confirm here, and I'll highlight it in yellow, is n plus 1 factorial is indeed bigger than n factorial, so we are going to be able to confirm the alternating series test here for letter A. Letter B was mentioned briefly, but just to show you the formal work for this, it's not alternating because this 2n minus 1 term does not create alternating terms. It will always create an odd exponent. And when you take -1 to an odd exponent, it will always equal a negative number. So these were not alternating, and that's the reason why. Looking at letter C, the reason this is going to be not alternating series test is even though the terms do alternate, which is confirmed right here, and I believe, if I'm not mistaken, the terms do get smaller because n over 3n plus 1, when you plug in n plus 1, the denominator is going to get bigger. The reason why this is an issue is that the limit as n approaches infinity does not equal 0. In fact, it equals 1/3. So that's the reason why this is going to be considered no. The last question that we're going to talk about here is the concept that he mentioned that kind of makes this difficult. There's not really a formula approach to this. What you have to actually do is write out some of the first terms, and that's what you do. So notice that the odd terms, you have to use 1 over n. So that's what's done here in blue and blue. And then the even terms, you have to use this instead. So the terms are indeed alternating. And the limit as n goes to infinity is going to approach 0 because in the piecewise function, both functions are going to equal 0. But as you are looking at the terms, they are not progressively getting smaller. In fact, it seems to be getting large and then small, and then large and then small, and then large and then small. And what's happening here is it's not actually consistently getting smaller over the course of time. It keeps going up and then down, up and then down. So we are going to be able to come up with a conclusion here that this condition is being violated. The next question we're going to look at is practice 2 from this, which was a card sort. You have 6 different series to look at here, and your single task here is determine if the alternating series test applies or does not apply. So the big things we want to look for first is, do we have alternating terms in all of these questions? And so I'm going to use my yellow highlighter to confirm that. A, it does, because -1 to the n will always alternate between positive and negative, and so will letter B, -1 to the n plus 1. Those are the two forms that are going to work, as well as in letter F here, -1 to the n minus 1. And again, if you're never sure of that, plug in 1, 2, 3, 4 for n and see if it creates that alternating sequence. So far, we've got 3 of them confirmed with that. And then letter E, same thing goes, okay? Now, it comes down to C versus D as our issue here. One of these two is not considered alternating series because the terms are not alternating. Funny enough, this one that does not have a -1 in it, this is indeed going to alternate. And you just saw in the previous example that I went over in example 4 where I did that. This term right here, though, being 2n, this is going to yield an even number no matter what. It's going to go 2, 4, 6, 8, 10, and -1 to an even power will always be positive. So this letter C is not going to alternate. So because of that, this is going to be one of the first ones that we're going to move into the non-alternating category. There is, however, one additional one, so I'm going to highlight this in red to tell you that it's wrong. The last one we have to consider is that when we're looking at an alternating series, the limit, and we've talked about this in the other problems, the limit as n approaches infinity of a sub n must equal 0. Well, when I go through that, and let's look through them here. 1 over n squared, check. And this one's out, so we're going to go straight down to E. 2n over n squared, now there are n terms in the top and the bottom, but because it's bigger on bottom, check. Moving over here, n to the 1/3 over n, it's again big on bottom, so check. This is 1 over n, check. We're going to have an issue right here, however, because this limit, the limit, as n approaches infinity, of 2n minus 1 over 7n plus 3, powers are equal, so you're going to take the ratio of the coefficients. It's equal to 2 over 7. This is going to be a problem. So of the 6, B and C would not apply to the alternating series test. However, letters A, D, E, and F would all converge using the alternating series test. The only other thing you would have to consider is to show that n plus 1 is indeed bigger. The denominator is bigger in n plus 1 than it is in n. In all 4 of these remaining cases, that is going to be true. And for the last section of this video, we're going to look at practice number 3. And in these 4 statements, there is something incorrect about each of them. You need to correct the statement. So in statement number 1, they state that a sub n plus 1 must be less than a sub n, which is going to definitely be true. However, the problem here remains that it says that the limit as n approaches infinity of a sub n needs to converge. We don't want it to just converge. Converge means it can be any number. We don't want it to be any number. It must be 0. So the correction in this statement is that it must equal 0. In the second example, they are only acknowledging condition number 1, which is right here. The limit as n approaches infinity of a sub n is equal to 0. That's condition number 1. There's no acknowledgement of the second condition of the alternating series test, which for convenience sake I've put over here on the right-hand side of the screen for you. You must also, in order for an alternating series to converge, you must show that the a sub n plus 1 term is smaller than a sub n, which is what we confirm in our corrected statement down below. In statement number 3, it says if an alternating series diverges, then the limit must equal 0. That is false because in order for an alternating series to converge, the limit must equal 0. So we're basically just going to change that word diverge to converge. And finally, in statement number 4, the series says that if a series diverges, then it is automatically true that the limit does not equal 0. If we actually go back to one of our previous examples, we showed a situation with that even and odd problem back in example, I think that was actually practice 2, I'm sorry. It was this problem right here, letter D. In this problem here, we showed that the limit can equal 0, but the series doesn't have to exist. So that'll conclude this supplemental video. I hope you found this time helpful. Please reach out if you have any other questions, and thank you for watching.